Hi there, this is our first look at exercise 8B. It's going to build on what we did last time on the addition formulae, or sometimes called the compound angle formulae. Now, notice one of these is actually on this little cartoon here. It's got, presumably, Sherlock Holmes talking to his best buddy, Dr. Watson. And it says sine 2 theta is 2 sine theta cos theta. This is a rule that you're meant to know, as is the one underneath it. But you know, hopefully you've seen that before as well. So, but this is what I mean by the double angle formula. Notice it doesn't say theta, it says 2 theta. So these have formulae in their own right. Notice this is an example of the cast diagram, written in some strange way. So anyway, a little starter. This is me trying to prove the formulae for you. These are the formulae that we saw last time. So just looking at sine A plus A, instead of sine A plus B. Now obviously what I'd get there is I'd get sine A cos, not B because I've called it A. So if I have rather than A plus B, I have A plus A, then it's sine A cos A plus cos A sine A. And what you'll notice is they really are the same thing. So you end up with two lots of sine A cos A. And, oh, that should have said cos. Now, why is that important? Because really, this is sine A plus A. This is another way of writing sine of 2A. And that's what this is. This is a formula, then, for the double angle formula. If we do a similar thing with the cos, notice cos, cos, now they're both A becomes cos squared A minus sine A sine B. Well, if B is A, then it's sine A, so it's sine squared A. And that's my formula for cos of 2A. Again, if I say that's really an A, this then becomes tan A plus another tan A over 1 minus tan A times by another tan A. And that can be written as, well, two of them at the top, 2 tan A over 1 minus tan squared A. So these are the three formulas then. So that's what we got. That's what we got, and this one hopefully says the same thing as well. Yes, it does. So these are the three formulae I want you to write down in your notes. Now, bearing that in mind, these formulas are not in the formula book, so you need to write them down. And I've suddenly got three for this one as well. Now, this is what I wrote down before. This is what I wrote down before, but I only wrote down this. So it begs the question, where on earth have these two come from? And the answer is, basically it comes from this formula that we've seen from year 12, which is that sine squared of some angle theta, usually actually it says cos squared at the front, plus sine squared, and it says is equal to 1. You should remember that, cos squared plus sine squared is 1. Now what this means is I can write down sine squared theta in terms of it's 1, and I move the cos squared over, I get 1 minus cos squared. Seen that before. And likewise you can do the same for cos squared. This is 1 minus sine squared. Now, bearing that in mind, I got cos squared minus sine squared. So if I choose to write it as cos squared, I can get rid of this sine squared and write it as, well, notice it says minus 1 minus cos squared. And the minus and minus is a plus, which gives me 2 cos squared theta minus 1. And you'll notice that's that formula. So if I get rid of my sines and change them into coses, I get this. And I can do the similar trick to get that. Perhaps you might want to try it and see if you get that formula. But these are incredibly useful. These two, particularly with things like integrations. These, you know, it depends. At some situations you want this, some situations you want this, some situations you want this. You will definitely be using all three of these things. So write them all down. Sine's easier, there's only one formula. Tan's easier, there's only one formula. But coses, there's three. So notice a little fact that just because it says double angle formula doesn't have to necessarily just say 2x and x. So for instance, I could have something which says x, and that means I can use x over 2. Now by that I mean if I have sine x, theoretically that's the same as 2 sine x over 2 cos of x over 2. Because all I've done is, normally of course I'm saying to it, it's sine 2x. And it's 2 sine x cos x. So, but the rule is only that this thing effectively is halved when it gets to there. So if I have sine x, I have to halve it, x over 2, x over 2. It could say 4 theta, 2 theta, so by that I mean sine 4 theta is 2 sine lots of 2 theta. Cos of 2 theta, that's weird, isn't it? I've got a double angle formula with actually a quadruple angle formula. It doesn't have to be cos, sine, it could be one of the cos formulas as well. So for instance, if I go on to this one, it could be cos of 3y. Now remember the cos formula, it said cos, well we had 3 of them, didn't we? We had cos of 2 theta, and I said it was cos squared theta minus sine squared theta. Now this works with 3y as well, but I've got half it, remember. So this would be cos of squared of 3y over 2. See the way I've halved that? Minus sine squared of 3y over 2. Or one of the other two versions of that as well. Now look, as I kind of hinted at before, we use these in a variety of situations, one of which is solving equations, one of which is identities and integrating functions. Definitely integrating functions comes up loads. So first of all, let's have an equation, sine 2x. Now this is the thing. Notice it says minus cos x, that's okay. This is the bit I don't like. So sine 2x, I come over and think, I've got 3 formulas. So I can write this as 2 sine x cos x minus a cos x is equal to 0. Notice that's my range of values. You could try to divide by cos x. It's not a very good option. Take out cos x as a common factor, and that gets you 2 sine x minus 1. Now, because it's something times something else is naught, either cos x is 0 or 2 sine x minus 1 is 0. And if I do cos x of 0, I have to effectively do the inverse cos of 0, and remember this is in degrees, so if you're not in degrees, make sure you are in degrees, and that gives me 90 degrees. Now this of course is one solution. You should remember that for cos of theta you get another answer at cos of 360 minus theta. These are rules that we've seen before, so therefore another answer that would be 270. This one really, if I rearrange it, gives me sine x equals a half, and the inverse sine of a half is 30 degrees. So again, I need to remind myself of this. Sine theta gives me another solution at sine of 180 minus theta. So if you remember that, 180 minus that is 150. Now I can always add on 360 onto my answers, but that will take me past in all those situations. So I think that's all my answers, and that is indeed all my answers. So next one, what's it got? Now again, I like this. The bit I don't like is the cos 2x. So I've got to get rid of the cos 2x. Now cos is the pain in the bum one, because I've got 3 choices. I can use cos squared minus sine squared, cos squareds, or sine squareds. Take your pick. Well, it's because I've got sine x's over here, I think I'm going to use the ones with sines. So rather than writing cos 2x, I'm going to write 1 minus 2 sine squared x equals 5 sine x plus 3. Now I want to get these onto one side. I might as well move everything to the right because this is negative. And if I do that, I'll get 2 sine squared x plus 5 sine x. That 1 becomes a minus 1, so that's plus 2 is equal to 0. Notice this. This is in radians. So very first job, shift, set up, and chuck it into radians. Use your angle unit and stuff. So anyway, I'm in radians now. I can also use the quadratic equation solver. If I use that, now I can get the answer that I need. So chuck that into your calculator, to the quadratic equation solver. Now when I do this, I'm just doing it now, I get sine x equals minus a half for one solution, and my second solution, so sine x is minus 2. Now this is impossible. You should know that sine x is always between 1 and minus 1, so no solutions. But this one there is a solution for. So if I just do that, technically that should have been with some equal signs. So anyway, it's the inverse sine of minus a half, and I get, oh, in radians, remember, as well. And I get a decimal. I'm not sure if I'm meant to get a decimal, but I do get a decimal. I get minus 0.479 to 3 significant figures. Now remember the rule is that for sine theta you get a solution which is also at 180 minus theta. Now 180 really is pi, so since we're in radians, so if I do pi minus that, now that effectively becomes a plus, pi minus the answer, I get 3.62. Now notice my interval says 0 to 2 pi, so my minus number is too small actually, so I've got to add, you always add 360 on to get your next solution, but 360 is 2 pi, so if I add 2 pi onto this, so if I add, it was minus 0.479 plus 2 lots of pi, and I get 5.80. Let's see what my answers were. Oh, I've got exact answers there. Should I have got exact answers? And of course, actually, yes, I should have done, because sine x, it gives me minus pi by 6. So therefore, adding on pi and doing those things with it, depending on what calculator you've got, I did use a cheap old calculator. But yours probably gave you minus pi by 6, and therefore if you add 2 pi on, for instance, you probably got 11 pi by 6 straight off, and it's told you that. And if you do the other trick, you would have got that as well. So hopefully those are okay. Now the last one before we stop, tan x plus this. Oh, right, now this is one of those ones. Look, this is double that. So I can use this formula, but it just looks a bit different. I've got to change this tan x. So I'm thinking of this as my 2x. So I'm thinking of this as x, and this as x over 2, and this as x over 2. So this means I write 2 tan x over 2 over 1 minus tan squared x over 2. Don't forget, then I write this, 5 tan x over 2 equals 0. I don't like it amount at the moment, so I'm going to move this over here. I get 2 tan x over 1 minus tan, oh, that's x over 2 by the way, tan squared x over 2 on the bottom equals minus 5 tan x over 2. That's it. Now this is where I simplify a bit and move that over there. That gives me 2 tan x over 2, and I times the 1 by this lot, which gives me minus 5 tan x over 2, and I times this minus tan squared over, which gives me plus tan cubed x over 2. Notice the x over 2 stays there like all the time. Now I can move this over here, and it gives me tan cubed x over 2. That becomes a minus 7 tan x over 2 equal to 0. And I think I'm going to straight away take out the tan x over 2 as a common factor, and that then gives me tan squared x over 2 minus 7 equal to 0. So just working this up here, that gives me tan x over 2 equals 0, or tan squared x over 2 and equals 7. So I square root, that gives me, well, this one is the easy one. This gives me x over 2 is 0. So I think my answer is x is 0. Is one answer. And interestingly, x over 2, if I did this, is really between 90 and minus 90. So with tans you can add 180 on, you get your next answer. And this one, you just be aware that when I square root, I get x over 2 is the, well, it's going to be, it's tan squared, so tan x over 2 is plus or minus root 7. Now that will lead to several answers, so you're going to have to inverse tan both of those to get your answers. So these are my answers, minus 99.6 and 99.6 plus the 0. See if you can get those. And then that's what we're going to be looking at. We're going to be looking at exercise 8B in class. Best luck.